and this is the lab report for Lab 5 on Faraday's Law. So this lab report will be broken up into several sections, starting with the problem, then the procedure, results, glow script, and conclusion. So the problem in this lab is that we are dropping a magnet through an aluminum tube, and we are checking what difference this makes versus just dropping a magnet normally. And so we will see that this actually makes the magnet fall slower than it would normally. And now we have to understand that we have some key concepts. First is the idea of a magnetic dipole magnetic field, which we all know, which is just that a bar magnet is a magnetic dipole, and so it creates a magnetic field following this equation, and we all know the visualization of it. Next is the idea that a changing magnetic field, such as one caused by the bar magnet falling, will induce an electric field in its surroundings. And if it induces an electric field in its surroundings, and its surroundings is an aluminum tube, well, then the electrons are going to flow through that aluminum tube, and this will create an induced current. And this induced current will be shaped like a ring all around it. And so Lenz's law tells us that the direction of this induced current creates a magnetic field opposing the change in the original magnetic field. We also have Faraday's law, which is that the change in electric potential around any path is the same as the change over time of the magnetic flux through that path. And finally, we have the magnetic force on a current by a magnetic field, which is just given by this equation on the bottom here. I delta L cross B is the magnetic force. Now, the procedure in this lab is we are finding the north end of the magnet, dropping the magnet through an aluminum tube while recording with the north end facing down, and rewinding to find the time it took to fall through the entire tube. And finally, we are calculating the average time of 5 trials for the magnet to go through the tube. And the average time is 2.2 seconds in our experimental trials. And now we have a computational simulation. And the computational model can be found at this following link. And essentially, it's just treating every single piece of the aluminum tube as a separate ring. And so when the magnet is close and falling through, there is a change in magnetic field, which induces a current in all the rings that are close enough for it to matter. And based on this current, there is a magnetic field, a magnetic force exerted on each of the rings by the magnet, because the magnet creates a B field, and the current is in the rings. And then the force by the current on the magnet is equal and opposite. And so we will see, so every single ring the magnet is going to exert a force on. And so the rings below the magnet is going to exert a force with a downward component. And so the rings are going to push the magnet upward. And so every ring above the magnet is also going to exert a downward component. And the component of the forces by the rings above the magnet are also going to push the magnet upward. And so by the results of this simulation, we can see a velocity versus time graph, and that it took 3.8 seconds inside the tube, which was much larger than it took for us to drop it. And to interpret the simulation, we have several things. First, the rings below the magnet are red, and they have counterclockwise current, and the rings above the magnet are blue, and they have clockwise current. And because red is under the magnet, the change in flux points downward, and so a counterclockwise current will create a magnetic field that opposes this. And vice versa for the blue current above the magnet. If we flip the magnet, there will be the same velocity and forces, but the currents are switched. Red will be clockwise and blue will be counterclockwise. Our magnet is faster in the real world than in the simulation, but we can try to fix this by repeating more trials and calculating the magnetic dipole moment with greater accuracy. Finally, we know that initially the gravitational force is stronger, as seen by the falling velocity. And while inside the tube, the magnetic and gravitational force are in equilibrium. They're net zero. And leaving the tube, the gravitational force becomes stronger again, which is shown by this velocity graph. Because inside the tube, the velocity is constant, and then as soon as it leaves, the velocity starts falling again. With less resistivity, because V equals IR and I equals V over R by Ohm's law, the current would increase. And therefore, the force on the magnet by the induced current would increase, so it would take longer to fall. With holes, some rings wouldn't have current because the current wouldn't be able to flow through. And so less overall current would have less magnetic force upward, which means the magnet would fall faster. Alright, that's it. Thank you for watching.